Hi everyone. When you get your stream data, it will be posted in an Excel file similar to this one on the Colab site. And Spencer was really nice and laid this all out beautifully for you. So hopefully it'll be very easy to follow as you do your t-test and rank abundance curves and Simpson's D calculations for the Rivanna and for the Steger. So you should look through this and make sure you understand what each tab is for and where all the different data points are so you know what you're working on. But the first tab includes some directions. The next tab will have data for Steger Creek. You can see here that the rank abundance in Simpson's D calculation is set out nicely, much like the dinosaur example posted to Colab and YouTube last week. So you can follow along with that video and do it step by step to calculate your Simpson's D for Steger, as well as what you need to create your rank abundance curve. It also includes the width and depth measurements and a place for you to average them and calculate standard error. Over here, we have our velocity measurements and then how to calculate discharge. So remember, calculating the average width, depth, and velocity will be used to calculate discharge for the Rivanna versus Steger, as well as the standard error. And then here are some qualitative characteristics, such as the appearance of the water and whether or not there was aquatic vegetation present, what the bedrock looked like, and the dissolved oxygen and temperature readings. So they're denoted by riffle versus pool. Remember in our intro to stream ecology, we talked about how these different microhabitats within a stream are interesting to look at as well. Then we have a tab for the Rivanna, which follows the same format, so you can calculate Simpson's D and rank abundance, your width, depth, and velocity for discharge, some qualitative characteristics, as well as temperature and dissolved oxygen and riffles versus pools. There is a tab for you to populate for Steger versus Rivanna to create your rank abundance or dominance diversity curves. And then there is a table to fill out with your calculated averages and standard errors for all of our measured factors for Steger versus Rivanna. And if you are in Spencer's section or in a TA section that is not using the long-term data, you will populate all of your raw data in this table here and use that to calculate t-tests. So to show you what that looks like, I've gone ahead and filled out for dissolved oxygen. So here is what I calculated for the mean and the standard error, and I will show you how to get a p-value. So again, following the format up here, I have Steger and Rivanna, and I have the raw data for the dissolved oxygen. Now to run a t-test, you will have to have your data analysis tool pack downloaded or solver if you're on a Mac. So you're going to go over to data. You're going to click on the data analysis function here. And now remember, we are looking for a t-test that is two-sample or two-tailed, assuming unequal variance. That's very important. So a two-sample or two-tailed t-test assuming unequal variance. You're going to click on that. Mine was pre-populated, so I'm just going to get rid of those. You can see alpha is already set to 0.05. That means we're operating on a p-value of 0.05, so you don't need to touch that. Now, variable 1 and variable 2 are assigned arbitrarily. It will essentially be Steger versus Rivanna. Just make sure that you consistently choose the proper one so that it sets it up in the right format throughout all of your t-tests. So I arbitrarily just always make Steger variable 1 and I make Rivanna variable 2. So for variable 1, I am going to highlight all of the dissolved oxygen measurements for Steger. And then for variable 2, I'm going to highlight all of the dissolved oxygen measurements for the Rivanna. So of course, excluding the mean and the standard error, you just want your raw data here. For my output, I'm just going to place it right down here so you guys can see, and then I'm going to hit OK. All right, and now we have this. First thing we want to do is check our means and make sure they're similar. So remember I made variable 1 Steger, and I made variable 2 Rivanna. All right, and we had a 10.75 mean. Yep, that's right for Steger. And for the Rivanna, we calculated an 11.86 for the mean. Yep, that's right. Awesome. Okay, so we used to do things with t-stats, t-criticals, etc., but nobody really uses that in their papers anymore since we all go operating off of p. So if there's something in your manual discussing that, feel free to ignore it. We essentially want to highlight the means for each of these streams so that you know what the overall mean is. And then we want the p for the two-tail. So remember, we ran a two-tailed t-test. So we want the p for a two-tail. Totally ignore the one-tail. So that is our p-value for the difference between these two means. So it's saying overall, the DO for Steger was 10.75 and the DO for Rivanna was 11.86, but that the difference in these averages is not statistically significant. So because 0.4 is much larger than 0.05, we cannot accept the hypothesis that these two streams should differ significantly in terms of dissolved oxygen. And then you want to go ahead and do that for all of these features. So temperature, discharge, width and depth. And for Spencer's Simpson's diversity, because you only calculate 1D for Steger and 1D for Rivanna, so one value for Steger, one value for Rivanna, you can't run a t-test on that because it's only 2 data points, and that is not good practice at all to run a t-test on that. So if you're operating on Spencer's section or with a TA that is not using long-term data, you won't be finding a p-value for Simpson's diversity. Now, if you're in my section or operating with a TA that is using the long-term data, operating on the long-term data, you will have a sheet like this, which includes the past year's calculated averages. So for example, here is temperature for Steger Creek and Rivanna, dissolved oxygen for Steger Creek versus Rivanna discharge and Simpson's diversity, right? And so what you will do is you will add your calculated averages for our fall 2020 year to this data set by putting them here where it's highlighted and it says enter your calculated averages. And then we will be running a t-test on all of these. So to give you an example of what that is like, I will just show you discharge. So I'm going to go back to my data tab, to data analysis. It still has the t-test highlighted for me. So a t-test, the 2 sample, assuming unequal variance. I'm going to hit OK. All right. And this always pre-populates. I'm not sure why, but I'm going to go ahead and get rid of that. Okay, so for variable 1, again, I'm going to arbitrarily assign Steger Creek to variable 1. So to run a t-test on discharge, I'm going to highlight all of the past year's discharge measurements for Steger Creek here in the variable 1 range. Now remember, you'll be adding your calculated values here, so you'll be highlighting all of that. For variable 2, I arbitrarily assign Rivanna River, so I will highlight the discharge for the Rivanna River. I'm going to set a new output. I'm going to put it right there. And then I will hit OK. So first things first, I'll just make that Steger and make this Rivanna so I don't forget. And then you will see the calculated means. And you'll want to make sure that that matches up to the, well, it won't match up to that mean, but you can run a mean here if you wanted to check it by doing something like this. It'll be a little different from Spencer's because we are using this long-term data and already using the mean from our last data. So we can see here that if I averaged all of that, it matches up pretty well. So the mean for Steger Creek will be 0.1 meters cubed per second. And for Rivanna River, it will be 30 meters cubed per second. Again, we're going to ignore the t-stats and all that, but we want to pick out our p to see, is this difference in means statistically significant? Is there a 95% chance that it is a correct difference? So we want to pick the p for the two-tail. Again, it's a two-tailed t-test, so we want to ignore all the others and make sure you pick the p for the two-tail. And we can see that it is highly significant, right? Is 0.000237, which is a lot less than 0.05. So there's a lot less than 5% chance that this difference in means is incorrect, right? So we are quite certain that this is a proper difference in means. So you can report that in this case, the RCC, which indicates that streams of different orders should have statistically significantly different discharge measurements, this was definitely true in our case. There is a huge difference and it is very significant.